R should be P. I think this is misprint because it's I think just location or other general symbols, but in this slide, P R should be P. So this is misprint. This R means the without direction. P means the phase encoding direction. So I have to change here. Yeah. So for the phase, zero phase encoding gradient, there is no difference of magnetic field along the P direction. So all spins has the same precession frequency. That means all spins has the same phase, even though the time elapsed. So for this case, the phase encoding waveform has the zero intensity of gradient strength, and for the one-step gradient pulse, that means the GP is a small GP, then the linearly varying gradient fields applied like this. That means that there are field variations along the P direction. So each spin has different precession frequencies. So after when the gradient pulse is ended, the spins has a different rotation position like this, and each position, rotation position, is proportional to the gradient field strength or the duration of the gradient pulse. Because the position of spin is the phase of spins, right? And the spin, as I said before, phase is the area of waveform, gradient frequency, precession frequencies. And if the gradient has the constant gradient, then this can be written, right? Is gamma G P and position P, right? And time T. So GPP is the magnetic field at position P, right? So this means that phase is proportional to the area of the gradient pulse. So the position of rotation position is the phase. So that means for this spin, this is a phase at this point, and this is a phase. So this phase is depends on the field strength and waveform duration T. So this large T is according to the this time. Okay. So after the this phase encoding gradient, after the phase encoding gradient, there is no magnetic field variations. So the spins are the position of spins are fixed like this. This is the final result of phase encoding gradient. Okay. After that, new gradient field, 2 times of phase encoding gradient is applied. Then each position, the rotation position is also determined by the gradient strength and duration of gradient. And the gradient duration is the same as before, but the gradient field strength is twofold. So the rotation position is 2 times compared to the previous spin. So because the center position does not change the gradient field strength, so always the spin position, rotation position is the same. But for the other point, the spin position varies according to the gradient strength and the time. So if the pace of this spin is pi, then this spin has 2 pi. So the pace varies according to the gradient strength. So this is this is the pi 1, then this is 2 pi 1. Okay. And different phase encoding is applied consecutively. So we can get the phase variation each position here. So for center position, the phase do not change because the magnetic field strength is always the same for any other gradient strength. But the other position has the variation of magnetic field strength and the phase changes. So if the time interval of each gradient applied has the same as TR, I will explain later about TR. Usually we call this as repetition time, because this phase encoding gradient is applied every TR time interval. So the phase variations in the time interval TR is pi 1, 2 pi 1, and 3 pi 1, and so on. So there are phase variations at this point, and we can get the frequency at this point by the relationship between phase and the frequency can be written like this, right? dt. This means that the rate of phase variation is a frequency, right? So at this point, phase variation rate can be determined by the phase difference during the time interval TR. But for this point, the phase variation is larger than this point, because this phase has if this phase has 45 degree, then this is 90 degree, and this is 180 degree. So this point has a larger phase variation rate than this point. That means it has larger frequency, right? So from this phase variation, we can estimate the frequency correspond to each position. So even though we encode the space information to this phase, we can estimate the frequency from the variation of phase. That's the principle of space resolving using the phase encoding gradient. So using this technique, we can cannot get the space information by the only one signal. So for this technique, we have to get multiple signals. Okay? So we get the signal using phase encoding, zero phase encoding, and we have to get the other signals using different phase encoding gradient strengths, and so on. So if we want to get the n spatial information along the phase encoding, we have to apply the phase encoding gradient n different phase encoding gradients. So this slide shows the spin movement according to the phase encoding gradient. So when you assume that the phase encoding gradient with a yellow waveform, and the gradient, applied gradient is shown here, then this spin diagram is written at time t equals 0. That means just before the phase encoding gradient is applied here. Okay. So at this time, all spin has the same pace because the slicer selection is just finished. That means the maximum signal comes from the slicer selection process, and by applying the phase encoding gradient like this, the spins rotate according to the precession frequency, which is distributed along the axis. I think I should be changed also here to P. So each spin has. Can I have? Thank you. It's very inconvenient using the mouse. At the center point, the spin has the same pace because the gradient, the field strength does not change. But for the other position, the phase encoding gradient determines the precession frequency. So, according to the precession frequency, the phase can be determined by the field applied gradient field strength and the duration of gradient the pulse plus t. So, the frequency of each position is determined by the phase variation rate. So we determine the precession frequency omega 1 and omega 2. As I said before, the phase time variation rate of phase is equal to the space frequency. So this is the example of the phasing by applying the phase encoding gradient yellow waveform. So this phase should be changed according to the various phase encoding direction. This slide shows the example of phase encoding gradient by varying the field magnetic gradient, phase encoding gradient strength. By another example, we can apply the phase encoding gradient using the same phase encoding gradient field strength, but by applying the varying pulse width like this. For the same magnetic field strength, we can apply the phase encoding gradient like this. Because the phase encoding is performed by the area of gradient pulse. So there are two methods. For fixed field intensity, by fixing the gradient strength GP, the variation of pulse width can be applied for the phase encoding. And for fixing the width of duration of gradient waveform, and by changing the intensity of gradient strength. So usually we use the fixed duration of gradient is frequently used because the pulse, the timing is fixed, but varying the amplitude of phase do not have timing effect. So sometimes the duration of pulse sequence is very sensitive to get the best imaging technique. So this page shows that each spins at different position has a different phase depending on the phase intensity and the phase duration and the position. So each phase has depends on the positions here. So here we define the k variables. K equal gamma n GP T. From phase equation, only space variable r is removed here. So k variable is determined by gradient strength and duration. That means the k is proportional to the gradient waveform area. So, and the reason why we define the Kn is that the Fourier transform equation becomes simple by applying the variable as space variable r and k. So the MR equation becomes simple, which is represented by the variable, only two variables, r and k. I will explain later. Okay. So this phase can be rewritten by k and r. Only two variables are represented. So this phase, as I said before, Fourier transform has the intensity and the phase, right? So this phase is represented by k variables and the position of variables r. So the MR equation becomes simple, and it can be simply easily compared with the familiar Fourier transform equations. So this slide shows the phase encoding gradient and MRI signal. Yeah. For the zero phase encoding gradient, all spins have the same summation of all these spins are large, right? This, but for non-zero phase including gradient, spins has a different phase here. So the vector sum is less than zero phase including signals here. So for large phase including gradient, the signals decreases according to the strength of phase including gradient. And all these signals are acquired using the frequency including gradient as explained here. That means this pulse sequence will be repeated with different phase including gradient, right? So using a zero phase including gradient, this signal is acquired using without gradient, and after that, the slice selection and the phase without gradient will be applied using different phase including gradient. That means every signal for different phase including gradient is acquired using the same slice selection gradient and without gradient with different phase including gradient. So I think this will be explained later. So this is the phase encoding equation again. So this is the also how can we explain the phase with the phase encoding gradient. So large GP can be represented by phase encoding gradient step GP, and n is index of phase encoding gradient. So n is integer value. Okay? And so n is minus 1 to 28 to 127. So for the phase including gradient, the signal phase according to the phase including gradient can be written like this. Omega RT is the phase, and omega R can be written by gamma NGP produced by R. So as I said before, gamma and Kn is defined by gamma GP large T. So this is Kn. So phase is K product by R. So from this equation, the MRI signal can be written like this. Phase is written by K and product by R. So this is a very familiar equation of Fourier transform, right? But the Fourier transform variable is K and R. Usually, the usual variables of Fourier transform is frequency and time, right? But this is the imaging equation. So for the imaging, the Fourier transform variable is space variable R and the spatial frequency variable K. So K is the spatial frequency. So that's why I called the raw data, MRI raw data as K-space data. Okay. So if we represent this phase as gamma N GPT R, then it's a little bit complex to understand as a Fourier transform equation. So using the K variables, we can easily understand that this equation is a Fourier transform shape. Okay. Yeah, this slide shows how can you get the MRI data using the MRI pulse sequence I explained before. So this 2-point dashed line is the pulse sequence for slice selection and the readout gradient. And this box is repeated many times and with different phase encoding gradient. Okay. So for zero phase encoding gradient, the signal is very large. So maximum gradient is obtained using zero phase encoding gradient. But for non-zero phase encoding gradient, signal reduces depending on the phase encoding gradient area. For the large phase encoding gradient area, signals reduces more. So for the matrix size of the image, the data acquisition point is determined by the image matrix size. So for example, if you want to get the 256 image data, then we have to get the sample of data in this direction, 256. And in the phase encoding direction, also the number of step of phase encoding should be 256. Is it clear? Okay.
For the GP.
GP means step of phase encoding gradient. And N is the index of phase encoding gradient.
Duration of N is from here to here?
Right.
Here to
From minus 228 to 127 is the range of N.
This one is straight.
Yeah, this one is a step of phase encoding gradient amplitude. So this is fixed. So phase encoding gradient strength is multiplied by small gp and n. Yes.
Is there any connection between the number, the range of n, and the grayscale?
The order of phase encoding can be changed. Yeah. Sometimes phase encoding varies from center to up, and after that bottom to up. Or sometimes phase encoding plus minus, plus minus, plus minus. It depends on the programmer. It's up to programmer. Okay. But there are some a little bit side effects depending on the hardwares and MR spin systems. So generally we use the alternative order of phase encoding steps from 0 to increase or decrease, because 0 phase encoding signal has a maximum signal. So when we first we get the largest signal, then if there are some problems later, then we can generally reconstruct the image even though it is poor. Yeah.
If n is minus, how about the shape of the signal? Is it better or still no?
It depends on the phase encoding gradient, frequency encoding gradient. Sometimes the signal has opposite polarity, but not always. Because the phase encoding gradient reduces the signal. So, and the spins has by applying the phase encoding gradient, one half of spin has a positive, but the others has a negative. So even though the polarity of gradient is opposite, so we cannot say that the signal polarity has an opposite. So it is very difficult. Some complex problem. Usually, large phase encoding gradient, the signal becomes almost disappear because all the phase of spins are different. So this is an example of MRI data. So for the large phase encoding gradient, all of the signal becomes zero, and there is several noises are here. For the zero phase encoding gradient, signal has a very, very large. So this is the case-based data. Sometimes we call the MR low data. So center line, the signal profile of center is shown here. So for the zero phase encoding gradient, here, zero phase encoding gradient, as I said before, all spin has same phase. So the vector summation is maximum. So the signal intensity is maximum for the zero phase encoding gradient. But for the non-zero phase encoding gradient, the phase has a different incoherent phase generates the reduced signals. So that's why the only center signal has a maximum intensity of signals. But for the large phase encoding gradient, the most signals are reduced like this. So in vertical direction has the same tendencies. So we write the MRI signal, the signal can be written like this. The rho x comma y is the spin distribution in the object, and the phase, each voxel has the phase like this. As we defined the k variables in x direction and y direction, so the MRI signal is written can be written using the Fourier transform equation like this. So the raw data is the Fourier transform shape of the image function. So the MR image can be generated by inverse Fourier transform of raw data. So we call this process as a reconstruction process. And this image is represented by image function rho x comma y, and we call this image domain as image space or spatial domain. And we call this domain as spatial frequency domain or k-space domain, because we use this domain variables by k variables as we defined before. So we call this variable domain as a k-space or spatial or frequency domain. So I think yeah. So this slide shows the relationship between the MRI signal and the phase encoding gradient. So for the zero phase encoding gradient, we get the maximum signal, and according to the strength of phase encoding gradient, the signal reduces. And after applying the phase encoding gradient, the without gradient is applied to get the MRI data here. So the order of gradient first, phase encoding gradient applied first. After that, without gradient is applied to get the MRI signal. Okay. So by rearranging the phase encoding gradient, corrected MRI data according to the order of phase encoding gradient step, alternative order or bottom to up order, everything is okay. Just we can rearrange the corrected data according to the index of phase encoding gradient from minus 128 to plus 127.